Today we're going to cover our second of our three units in mass and energy balances. Today we'll be talking about incorporating chemical reactions and phase equilibria into our mass balances. By the end of this video, you should feel comfortable with reactive systems, including excess and limiting reagents, percent excess and conversion, and then using irreversible and reversible reactions in equilibria and then incorporating both of these concepts into your mass balances. We'll then talk about atomic species balances and multi-phase systems. Within there, we'll sort of review phase equilibrium. We'll talk about Raoult's law, Henry's law, Anton's equation, the Claudius-Clapeyron equation, and diagrams for obtaining phase equilibria. And then I'll show you an example of how we can incorporate these into our mass balances. All right, let's start with a review of stoichiometry. So as a reminder, the stoichiometry or stoichiometric ratio is a ratio in which chemicals combine in a reaction. So, for example, if I have 2 moles of, it takes 2 moles of SO2 plus 1 mole of O2 to form 2 moles of SO3. Right? So this is just saying by having these numbers up front, right, our stoichiometric coefficients, that SO2 and O2 are going to react in a 2-to-1 ratio, and SO3 is formed from SO2 in a 1-to-1 ratio, and then of course SO3 be formed from O2 in a 2-to-1 ratio. Okay, so let's in reactions in chemical engineering systems, in general, we don't have a perfect 1-to-1 molar ratio or a perfect stoichiometric ratio. We usually don't have exactly what we need. So we usually have an excess of at least one of our reactants, and then at least one we're deficient in. So let's have some definitions. We have our limiting reactant, our limiting reagent, which is the species that's used up first, or in other words, the species that there's not of. In other words, there are fewer moles than needed to fully react the other reactants. The excess reagent or reagents are the species which are left over when the reaction stops, i.e., all of the species which are not the limiting species. All right, let's do an example looking at limiting and excess reagents. So let's say we have 4 moles of SO2 and 9 moles of O2. What is our limiting and excess reagent? And then what is the percent excess? Right, so if I have my reaction, I require 2 moles of SO2 for every mole of O2. Right, so I need a 2-to-1 SO2 to O2 ratio. To determine which one is limiting, we can assume that each one is limiting and see how much of the other we would need. If SO2 is limiting, I would need to have at least 2 moles of oxygen, but if oxygen is limiting, I would need at least 18 moles of SO2. So if I look at this, I can say that I don't have 18 moles of SO2, so oxygen can't be limiting. Let's look at SO2. Do I have at least 2 moles of O2? I do. So that means that SO2 is limiting. All right, so the percent excess is what I have minus what I need over what I need. We need to look at percent excess oxygen. I have 9 moles of oxygen. I only need 2 moles of oxygen. So then I have 350% excess of oxygen. All right, so usually things rarely fully react. So we often have to think about conversion in chemical systems. So conversion is the fraction of a reagent that fed into a reactor that actually reacts. So conversion, or sometimes we refer to this as X, is the moles reacted divided by the moles fed. Or in other words, the moles that go into the reactor minus the moles that come out of the reactor over the moles that went into the reactor. So again, looking at our SO2 plus O2 case, if I feed 100 moles of SO2 into the reactor and I get 20 moles of SO2 coming out, I can look at the SO2 conversion by taking 100 moles that went in minus the 20 that came out over the 100 that went in. I have an 80% conversion of my SO2. If I do the same thing with the oxygen, I had 90 moles go in, 50 come out, 90 went in, so I have a 44% conversion of my oxygen. Notice that these two are not necessarily equal in the system, right? And nor do they need to be in a stoichiometric ratio. This is because they're not necessarily fed into the reactor in a stoichiometric ratio. Okay, so let's delve a little bit further, thinking about chemical equilibria. So we have sort of two types of reactions that we think about: irreversible reactions, which only proceed one way. And so these are going to go until the limiting reagent is consumed, right? So it's going to go reactants, go to products, but products can't go back. And then we have reversible reactions where A plus B can go to C, but then C can break back into A and B. And so these reactions are going to continue until an equilibrium is reached as defined by the equilibrium constant K. And K is, of course, the product of the mole fractions of the products and a product of the mole fractions of the reagents. So once again, if we're thinking A plus B goes to C, I have K equals YC over YA times YB. And of course, as you remember from general chemistry, K is a function of temperature. We're going to see here very shortly how we can use these in mass balances to help us understand a chemical system. All right, so let's get into it. Let's go and use that exact reaction. A plus B goes to C. And for this first example, we're going to assume that the reaction is irreversible. Right, so once A and B react, it's going to go to C. All right, so let's assume that the reactor achieves 80% conversion of A, that the influent stream has a 10% excess of B, and 10 moles of C per hour are produced. We want to know what the molar flow rate of A and B into and out of the reactor are. Okay, so previously, from last time, we didn't have enough information to solve this, but now that we know a little bit more about reactions, we do have that information. All right, so what do we always do? We start by drawing a picture. So here's my reactor. I have stream 1, stream 2 going in, so we can call these, A and B. I have stream 3 leaving, so that's going to be my product stream. I know that I have 10 moles per hour coming out. And here we're going to use this N dot symbol. So this is indicating molar flow rather than mass flow. I'm sorry, this should be an N of C because it's a molar flow rate. All right, I'm also going to write down that the conversion of A going to C is 80% and the excess of B is 10%. We're going to just keep those by the picture so that we have all the information we need in order to solve these problems in our handy dandy chart. Okay, so what do we want? We want N1, N2, N3, N3A, and N3B. Essentially everything we don't know. What do we know? We know how much C is leaving. We know the conversion of A, and we know the excess of B. Right? Once again, I really want to note that unlike mass balances, the flow in plus flow out, molar flow in plus molar flow out is molar flow in is not equal to molar flow out, right? Because they have reactions, right? In this case, I'm going from 2 moles to 1 mole. Okay, so let's write out our equations that we know. So I know that the conversion of A to C is 80%, so that's N in minus N out over NA in. I know that the excess was 10%. I'm going to assume that stream 1 is fully composed of A and stream 2 is fully composed of B. Okay, so now let's go ahead and let's write out our mole balances. Again, we're going to use accumulation equals input minus output plus generation minus consumption. So previously we had said that generation and consumption were 0, but now those are no longer true, right? This reaction, A plus B goes to C, is going to start cropping up in our generation and consumption terms. So if you look at species A, um, if we're at steady state and continuous reactor, there's no accumulation. The amount flowing in is Na1, the amount flowing out is Na3, and nothing is generated, but there is consumption, right? So we have Na reacted. We can then do, of course, the same thing with B, where I have no accumulation of B, just like A. I have B coming in, I have B coming out. And of course, if A is reacting, B must also be reacting. And then lastly, I do my mole balance on C. I have nothing accumulating. I don't have anything coming in, but I do have C coming out. And then I have how much C reacts. Okay, and based on the problem statement, that is 10 moles an hour. Okay, and so lastly, we can start making additional relationships by reminding ourselves, based on the stoichiometry, that NC reacted or generated is the number of moles of A consumed and the number of moles of B consumed. All right, so let's use these facts. Let's start plugging them in so I can take the number of moles of A reacted. Sorry, let me just go back and show you. Right, I can rearrange this to get the number of moles reacted on the other side. And so the number of moles of A reacted is the number of moles A in minus the number of moles A out, and we know that that's 10. Excellent. We also know additional information about A, right? So this reaction extent or conversion extent is 0.8. So that's A in minus A out over A in. Well, A in minus A out, I know what that is, right? That's 10 moles. So 0.8 equals 10 moles per hour over A in. Rearranging this, I know that A in or N1, Na1 or N1 is 12 and a half moles per hour. Okay, and so the number of moles, we can now look at B. The number of moles of B that we need coming in is, of course, the number of moles of A coming in. And I can use my definition of the excess in B. So the excess of B is 0.1. I have NB in minus NB need over NB need. Well, I know how much NB I needed because I know how much Na came in. So I can plug in that definition and we can find out that we have 13.75 moles per hour of B flowing in. All right. So this gives me the amounts coming in. I can now look at, how much is flowing out through these streams. Remembering our mole balances, right? We have Na in minus Na out minus Na consumed is 0. So the Na out is Na in minus Na consumed. I know what came in, right? It's that 12.5. I know it was consumed. It must be those 10 moles per hour, right? Because that's how much C I have. So that leaves me with 2.5 moles per hour. And then that's of course our Na3. Okay, I can do the exact same thing on the B side. I had 13.75 moles per hour going in, 10 moles being consumed. So there's 3.75 moles of B in stream 3. All right, so we have our final solution. Okay, now let's go forward and do a mole balance, looking not at a sort of a reaction that is sort of irreversible and or defined by the extent of reaction, and rather look at an equilibrium process. Right? So we could have in a reaction that the reaction reaches equilibrium. So let's assume that we have a gas reactor that's sitting at 100 degrees C. The reactor runs to equilibrium, and our equilibrium constant is 2. Let's solve for the flow rates of B. Let's solve for the flow rates if B is fed in a 10% excess. Here, we're not going to go all the way through this problem, but we're going to sort of set it up and get to a point where it becomes just a simple mass balance, which we have become familiar with. Okay, so setting this up right, we have our reactor equilibrium K, which is equal to the partial pressure of C over the partial pressure of A and B, right? Because we're not going to, if we assume that there's no volume expansion in the reactor, all of these are at the same, um, volume. The temperature isn't changing, so we can um, directly relate, the relative pressure to the number of moles. Okay, so we can say that 2 equals 10, right? Because that's what's coming out of here. Um, so that's how many moles we need going through here. So 2 equals 10 over N3A, N3B, right? So these are referring to the extents leaving the reactor, because what's leaving the reactor is what's in equilibrium. I can rearrange this to say N3A equals 5 over N3B. And now I have the information, right? I have all the equations that I need to go back and solve my my equations using a mass balance, a mole balance. I'm going to leave this for you as practice because um, you now see how we can incorporate equilibrium into getting concentrations. And once we have concentrations, you should be familiar by now with how to deal with those in mass and mole balances. Okay, so in addition to mole balances, we can also do what are called species balances. Here, instead of looking at the number of moles or the mass of things flowing through, we're going to look at the molar flux, or the molar flow rate of individual atomic species. So let's just go ahead and consider that we have hydrogen and oxygen going into a combustor. And let's say that we know coming out we have 1 mole of water, half a mole of O2, and 0.1 mole per second. All these should be per second of H2. And let's just pretend for a second that we don't know what the stoichiometry of this reaction is. We can still figure out how much H2 and O2 went in. So we're going to do this by looking at a mole balance on the individual atoms. So we're still going to say accumulation equals in minus out plus generation minus consumption. In a continuous steady state reactor, once again, no accumulation. And then if we're thinking about not in terms of molecular species, but rather on an element-wise set, we should have no generation and no consumption because we're not dealing with nuclear reactions. So let's first look at the hydrogen mole balance. So the amount of accumulation is 0. What's coming in? Well, the number of moles of hydrogen atoms going in is 2 times whatever the molar flow rate of N1 is, right? Because there's 2 moles of hydrogen atoms per every mole of H2. Okay, let's look at the output. Um, what's coming out? We have 1 mole of water. In each mole of water, there's 2 moles of hydrogen, so we have -2 times N3. And then we also have some H2 that's coming out. So once again, 2 times NH, 2 times N3H2. Okay, I can do the same thing for the oxygen balance. There's no accumulation. There's 2 moles of oxygen for every, there's 2 moles of atomic oxygen for every mole of molecular oxygen. So we have twice N2 minus 1 times N3 because there's only 1 mole of oxygen in each mole of water, minus twice the molar flow rate of molecular oxygen in that output stream. Okay, so if we sort of notice, we have our streams, our species-based stream flows, and then in front of each of our flows, we have the stoichiometric ratio of our molecules. All right, so when we're doing this, we can plug in our numbers. So 2 times N1 minus 2 times 1 minus 2 times 0.1. That means that 1.1 moles of H2 must be going into the reactor. Similarly, I can write this out, and we can say that N2 is 1 mole. All right, and so even without knowing, that water reacts in this, or hydrogen and oxygen react in a 2-to-1 ratio, we can um, sort of include or sort of get around that and do a molar balance of this system. All right, so I now want to move away from thinking about reactions. You now have enough information to be able to solve any reactive systems mole balance using either molar balances or species balances. And I now want to think about multi-phase flow. Um, so let's take an example of a multi-phase flow. So let's take a flash unit. So a flash unit is something that uh, would either heat up or cool down something so that we reach a new equilibrium point. So let's say that we have liquid that's 70% water, 30% ethanol. It goes into a flash unit that's operating at 88 degrees C. We establish equilibrium. I pull the gas off the top, and I have liquid that comes from the bottom. Um, and so we can use phase equilibria of what's leaving this system in order to sort of help us do these mass and mole balances. I want to make a brief note of common notation in chemical engineering. Um, when we're talking about mole fractions, we want to think about mole fractions in the gas phase and the liquid phase, right? So as a reminder, a mole fraction, right, X would be the number of moles of species I over the total number of moles in a stream. It's the same in the gas. But just to sort of help us keep track of what's liquid and what's gas, we often write the liquid mole fractions using Xi and the gas mole fractions as Yi. Okay, so we can figure out, given this, all we need, sorry, to solve this mass balance, as we've seen multiple times, is the composition of these gas and liquid streams. And we can get that through things like a phase diagram. So here's our flow diagram, and here is a phase diagram of ethanol mixed with water. So if you're unfamiliar with how these work, here at the bottom, I have the fraction of ethanol. And so then the fraction of water in the stream is just one minus, or sorry, the percentage of ethanol. So then the percentage of water is just one minus that. So at this point where it says 20, that's 20% ethanol. It would be then 80% water. So along the y-axis is the temperature of the system, and then the blue, in this case, and red curves mark uh, the sort of phase equilibrium. So anything above the red curve is going to be all vapor. Everything below the blue curve is going to be all liquid. If I sit between the red and the blue curves, um, I have a mix of both the vapor and the liquid. When I'm doing a flash unit, I often want to separate things, right? I want, some new fraction of water and ethanol in one phase and say water and ethanol in the other phase. And so I want to be working in this envelope, which is gonna, say that there's some liquid and some vapor. Um, so if I were to take, or when I take this mixture of ethanol and water, right, I can go on here. I have 30% ethanol. That's this line. Um, and I can say, okay, I'm operating on this point. I'm going to go all the way up to the temperature that I'm working at. And then I'm going to draw this, we can call it a tie line, right? So I'm working at this temperature. This is what's entering my stream. And then my stream is going to break into two components. One is going to operate at this composition. My vapor phase is going to operate at this um, composition. My liquid phase is going to operate at this composition. Okay, so if I look at this, I can, go across the tie line to my liquid phase. I see where that line intersects with my liquid line or my liquidus line. I come down and then I can read off the percentage of ethanol. And in this case, I'm estimating this is about 13%. So we can say that the mole fraction of ethanol in the liquid phase, and we know it's liquid because I'm using an X, is 0.13. Of course, that means that the fraction of water is just one minus that, so it's 0.87 or 87%. All right, so if I want to now do the same thing in the gas phase, I merely go over to the gaseous line. I go down. In this case, I have 40% ethanol and therefore 60% water. All right. So now that we have this information, we can solve the mass balance, right? I know my fractions in the gas, my fractions in the liquid. I can now solve for my total flow rates, etc. Okay, we're not going to do that because you already know how to do that. I'm just going to make a few comments. If I was operating at 88 degrees C once again, and I was at already 60% ethanol, it's just all going to be vapor, right? So the flow rate out through the liquid would be zero. Everything would come out in the gas. Similarly, if I was operating at 88 um, degrees C and I only had 5% ethanol, I would have no vapor. Everything would be in the liquid phase. Okay, so this is the general, whoops, sorry. This is the general idea of phase equilibrium in mass and molar balances. I use my Equilibria information to determine what the mole fractions are in the different phases, right? So I know how things are going to separate. Those phase diagrams are only one of multiple ways that we can obtain the necessary phase equilibrium. So the key equations that we're going to sort of go through today are things like Raoult's law, Henry's law, Antoine's equation, and the Clausius-Clapeyron equation. You could also look up information in tables. So think, dew points. But these are the ones that we're going to cover. All right. So Raoult's law says, given an ideal solution. So, right, let's say I have, once again, ethanol in water, right? I have a pure solution. The partial pressure of species I above that solution is the pressure above that solution if it was 100% pure, right? So instead of having a mixture, if I had pure ethanol, I can take, whatever the partial pressure is expected to be at the temperature I'm operating at, and then I multiply that by the mole fraction in the solution. Okay, so once again, often these partial pressures of the individual species, or sorry, the expected partial pressure of the pure species, so this pi star, um, is either tabulated or, as we'll see in a few seconds, there'll be equations to deal with that. And so then if I have mixtures, Raoult's law will give me a way to take those information about the pure species and apply them to mixtures. All right, so sort of in a similar fashion, there's Henry's law. So let's pretend now that I have a species that's in the gas. So, I mean, this could be, you know, CO2 going into soda, right? So I have CO2 sitting above there. Henry's law will tell us how much of that CO2 is going to go into the solution. And so the concentration of, say, the CO2 is equal to Henry's constant times the partial pressure of that species in the gas phase above. Right. And so this generally works when the concentrations are small fractions, right? So we're talking, 1% or 2% or, less, not, a 50-50 mixture. In a 50-50 mixture or something along those lines, we need to be using Raoult's law. Okay, yep. So Ci is the concentration of species I in the solution, H is Henry's constant, and P is the partial pressure of the species of interest. All right. So I said earlier that there were equations um, that would tell us uh, what we can expect the partial pressure of a liquid over, sorry, the partial pressure of a vapor over its liquid would be in a pure phase. And so Antoine's equation is the most standard way of sort of representing that. There are more complicated versions, but this works pretty well, and you can find these tabulated values relatively easily. So this says that the partial pressure of species I over its pure solution, so no mixtures, just say, pure water, pure ethanol, pure butanol, whatever. The log of that is equal to A minus B over C plus T, where T is our temperature. And A, B, and C are constants. Okay, so what you would do is you would go to a table or a database. You would look up hexane, octanol, whatever you're interested in, and they would have these constants A, B, and C, and then you can find out what the pressure is of that species as a function of temperature. Okay, so it's possible as well that you don't necessarily have those equations, those A, B's, and C's. You have some sort of new species, and you've measured um, the partial pressure of that species at one temperature, and you know the heat of vaporization, you can predict the partial pressure at other temperatures. So, sorry, these should be 0 and 1, not 1 and 2. So, if I know the partial pressure of you know at one point I can use this equation. Um, R is our gas constant. L is the molar heat of vaporization, right? So um, how much energy, kilojoules per mole, um, are required uh, to vaporize that, and then I can use, um, you know, plug in the temperatures to get whatever I want, as long as they're in Kelvin. All right. So, just sort of as a summary, how can we incorporate multi-phase flow and phase equilibria into mass balances? Um, it's pretty straightforward. We use the phase equilibrium either by the phase diagrams or various equations, and that will tell us what the fractional compositions are when I have or when I'm in the equilibrium. Once we have those fractional compositions, we can then do mass mole or atomic species balances, as we've been doing in this class, both this lecture and the previous lectures. Okay, so that's it for mass and molar balances. You should now be familiar with, in reactive systems, the idea of excess and limiting reagents, percent excess and conversions, irreversible and reversible reactions and equilibrium, and of course, how we can incorporate this information into um, mole and mass balances. We also talked about atomic species balances, where we say that individual uh, atoms cannot be created or destroyed, and therefore we can perform um, balances on the total set element by element. Of course, we can mix and match. We can do some elemental balances, some mole balances, some mass balances, right? All these things can be mixed and matched to pull out the information we need. We also then talked about multi-phase systems, so how we can use information about phase equilibria to determine um, speciation in various systems that are at equilibrium, and then we can use that to solve mass balances, mole balances. We did so, and we provided sort of um, four or five different ways of doing that. So, phase equilibrium uh, tables or diagrams, Raoult's law, Henry's law, and then Antoine's equation and the Clapeyron equation. All right, with that, that's going to wrap up our units on mass um, balances. Next time we're going to do we're going to do um, energy balances, and then we're going to move into fluid mechanics. As a reminder, please take the quiz, and I will see you next time.